Good morning, everyone. We'll get started this morning. Before we get started on this problem, I want to take a couple minutes to talk about scores in the class, how you guys are doing, how to kind of think about your performance so far in the exams. I know we can't yet see midterm scores. Once you see your midterm score, know that the average on the test across our Chem 1210 sections appears to be in the range of about 75%, which is kind of typically where we see the midterm 2 average. I mentioned after midterm 1, usually midterm 2 drops a little bit. The material does get a little bit harder. Also, sometimes we get a little bit complacent. Sometimes midterm 1 goes so well that we think this class is so easy, and then we don't put a lot of effort into studying. So some of you guys may have been caught off guard. If you were caught off guard for midterm 2, we can talk about a couple strategies. But let's just talk about first, the point allocation in the class. It's in the syllabus. I think we've talked about this before, but I just want to make sure that we know kind of how the class is broken down. So we have midterms 1 to 4. Those are 10% each. So of course that's 40% of the class. Our final is 20%. So that's, another 20% of the class. So exams in total are 60% of the class, but the other 40% are things like lab. Lab's 20%. Homework, the post-lectures is 10%. Coming here or doing the lecture tutorials in place of lecture attendance is 5%. And then recitation is also 5%. Most people are getting like 99% on average in recitation and in lecture. So, we're not having and seeing students by and large not attending lecture. Most students, I'm seeing about 90 to 95% attendance or tutorial assignments done for every lecture. And the 5 or 10% seems to be a slightly different crop of students. So we only have a handful of students who've already gone through their 6 misses. If you didn't know, or if you forget, you get 6 lecture misses throughout the semester. So if you forget the lecture assignment and to come to class, you get 6 chances and not have to worry about missing class or doing the tutorials. But in total, and then for recitation, you get 1 absence if you didn't know that. You get 1 absence or 1 drop score from recitation. Homeworks are kind of like we count all the assignments. But again, check your scores on these assignments. Check your, in Carmen, you can see your average. To give you an idea, lab average is like 93%. I know lab is tricky. There's a lot of components of lab. There's a lot of assignments, but generally high averaging scores if you put the effort and energy into figuring out what you need to do, when to turn it in, how to do those assignments. If you get stuck on lab stuff, the Learning Resource Center or the office hours and 205 Celeste, great places to get help. Homework, again, if you get stuck on homework, definitely check out the readings. Most of the problems are in the readings. I think going through the readings is very helpful to kind of couple with lecture. And then finally, in total, 40% of the class, relatively easy to get those points. So, the average across lab, homework, lecture, recitation is in the 95% plus range. So definitely you don't want to be in the category of losing ground in the class on the easy to get points. So that gives you a little bit of a buffer. So the way I like to look at midterm scores is if you're north of 80%, you're doing really, really good in the class. You're heading towards a grade. If you're above an 80% average, you're heading towards a grade, and as long as you're doing the other 40% of the class items, you're heading towards a grade in that B+, A-, A range, depending, specifically on how well you're doing. So you don't have to get 100% on exams. The goal shouldn't be perfection with exams. It should be getting into that 80% plus range. A test or 2 might be lower. The thought should be, how could I have maybe better approached, reading through the chapters, studying the chapters, understanding the material to best prepare for midterms. I think the one area that most scores that are in the lower range the common feature is usually not a lot of time spent practicing problems with the book closed. It's hard to do homework problems with the book closed. In fact, I think post-lectures you should have the book open. That's the idea. But you should do some daily quizzes, some practice exams to really help prepare you to be in that test-taking mode. So spending time, I think slowly too, is helpful. I think doing those practice quizzes like this week, next week, the week after is really helpful for just getting into that test-taking mode. Having practice recalling information is actually not easy. So being used to sort of recalling all the information across a couple chapters will really help you come time for exams. That's going to be much better than just doing the practice exams like the night before the test. For slowly doing some practice problems. So approach the daily quizzes, close book, close note, close internet. Try to force yourself through most of those problems. The ones you're stuck on, instead of trying to say, well, just how do I do the problem? How do I memorize it? Try to think, well, what do I need to know? What was I supposed to know and apply in the problem, so that hopefully when you see a question like that on the test, you have a good chance of getting it correct. The last thing, a couple of last things I'll say is that the couple of features I saw that were common in scores that were on the lower side was not doing the practice exams at all. So that was a good indicator of just lower exam scores on average. Now, some students did skip the practice exams, or maybe on my end, maybe some of you guys study together. So maybe not every individual student downloaded and actually did the Carmen quiz of the practice exam. So maybe some of the data isn't possible for me to see. So if you're working with a friend and you never actually entered the answers yourself, so maybe you really did the practice exams and I just don't know it. So there are some students who didn't do the practice exams that did really good on the exam, but on average, those who didn't do the practice exams, the scores were a fair bit lower. Homework was actually, the post-lecture assignments are actually another big indicator, because I know they're only worth a small amount of points. So maybe a few students in the class are like, well, I'm not gonna worry about the 5% of the class because it's such a small amount of points. It turns out that those with a really low homework score also had a pretty low exam score. Now again, causality is weird, right? It doesn't mean that not doing homework caused you to get a low exam score, but it's sort of like motivating yourself to do the homework is gonna probably motivate you to do some extra studying, extra reading, extra problem solving, and all of that sum total work is going to result in doing better in the class. Every semester I'm asked to give a progress report for students that I get sent a list of students I have to say who may or may not be at risk of failing the course. So I just like to be upfront to say that what I identify as being at risk for potentially getting a grade in the E range at the end of the semester would be having exam scores below 40%. So if your scores are less than 40% on the midterms, that's where, come see me, let's work out a plan to get those scores up. But if you get exam scores above just 40%, usually you get a grade in the passing range. Because we have so many extra points to kind of like pad your scores with and to buffer scores. So as long as you're getting north of 40%, we can get you through the class. Let's try to get to 80%. Let's try to get there, and we can. Come see me if you have questions for that, and if you want to come up with a plan. And then also lab. So lab, you have to get a 50% or higher to pass the class. So if you're below a 50%, it's an automatic E, so just be aware of that. So lab scores have to be above 50%. And then just overall in the course, you get the pass grade, the D grade minimum is 54% overall. If you look at our syllabus, we have a grade scale. In fact, this will probably mess the video. So I just want to take that detour to talk about how you might be doing in the class, how you can think about your performance so far, study habit suggestions again. Focusing on the reading, focusing on trying to understand problems with like the post lectures. If you like to do the tutorials, that's helpful too. If you find those to be helpful, check those out. But then putting that together into practice exam problems through the daily quizzes, practice quizzes, AI quizzes, practice exams are a really good way to help prepare for exams. Okay, so off of that topic, we'll head back into chapter 5. So we're in the middle of chapter 5. We spent so far 2 lectures, or about 2 lectures, talking about chapter 5 and talking about like energy, heat, and work. We're going to sort of stop talking about work. We tried to introduce work, I think, to talk about how that's the energy associated with putting objects into motion. And then we kind of dwindled down to, well, most chemical systems aren't doing much or any work. The open system really isn't capable of doing work because it's not really pressing on anything. So the open chemical system, like an open container, we saw that the heat change of that process is what we call the enthalpy change of the delta H. And then we'll see a problem, hopefully today, if you enclose that reaction and have a constant volume reaction, it's so close that we assume the heat change is still the enthalpy change. So delta H is the heat change that accompany reactions exactly in open systems and very closely related to the heat exchanged within a closed system as well. Okay, so we're going to calculate here in this problem the heat released or absorbed when hydrogen peroxide H2O2, 5 grams of it decomposes at constant pressure. Now the idea of constant pressure is that's just the one telling us that this is the open system, where our delta H is just simply equal to the heat changed by that process. Now sometimes you see the little symbol P for the Q, so you see Q sub P, that just means the heat change at constant pressure. And a lot of times we'll just write this as Q, I don't know why I have such a hard time writing a Q, but it's the delta H to the Q of reaction. So QP, Q reaction, these are kind of the same things. So this is like the heat change that accompanies a chemical reaction. Now, delta H, when you see it written with a reaction, sometimes you might see a little not symbol written with it too. The not symbol would just assume standard conditions that we'll not get too much into. But the idea here is that it's just the enthalpy change for the chemical reaction as written, where the big detail is that the reaction as it's written, the coefficients are assumed to be moles. And so this energy here, minus 196 kJ, says that for when 2 moles of hydrogen peroxide, precisely 2 moles, forms 2 moles of water and 1 mole of O2, then the delta H for that change and that amount of reactants is minus 196 kJs. One of the things we're seeing at the very end of class is if we were to cut all these coefficients in half, delta H is extensive, we would cut the delta H in half. If we were to double all the coefficients, we'd have to double the magnitude of delta H. So delta H depends on the quantity of reactants, and it's the amount of reactants are given by the coefficients assumed to be moles. And so that's the big thing here, is that whenever you see delta H for a reaction, is that we're assuming the coefficients are moles. And now when we think about 5 grams of hydrogen peroxide undergoing a decomposition, that's different than 2 moles. So we're going to have to figure out sort of by ratio of the minus 196 to say 2 moles of H2O2, we'll have to figure out what the heat change was for the reaction in terms of just 5 grams reacting. So one way I might go about solving this problem is that this delta H here is equal to the heat change of that process that's taking place. And then I can try to calculate the Q reaction when I have a different quantity. So I can try to calculate my Q reaction when I have just the 5 grams of hydrogen peroxide present instead of the 2 moles. If this problem said with 2 moles, what's the energy associated with 2 moles undergoing a decomposition? It would be minus 196 kJs. Now we'll have to think about given off or absorbed in a second, but I'll come to that question in a minute on whether heat's being released or absorbed in this process. Let's actually think about that right now. The delta H is negative. That means that this reaction, of course, is exothermic. Now, what does exothermic mean? Is heat being released by this reaction, or is heat being given off? Or is heat released by this reaction and given off to the surroundings, or is heat being absorbed by this reaction? What do you guys think? Released, yeah. So negative means the reaction's losing that energy. The energy has to go to the surroundings. So heat's being released by this reaction, and we're picking that up just by the negative delta H and the fact that we have an exothermic reaction. And so heat's not being absorbed. Absorbed would be a positive delta H, and we have a negative one. So we know that heat's being released here. So calculate the amount of heat that's being released. Back to the stupid pen being... Okay, I think we're back in business here. Okay, so let's try to calculate the actual amount of heat being released by this 5 grams. When I have 5 grams, it's going to be less magnitude than minus 196 because 5 grams is much less than 2 moles of hydrogen peroxide. So the next step that I want to undergo is converting grams to moles because I'm going to want to use the conversion factor that it's minus 196 kJs per 2 moles of hydrogen peroxide. So this conversion here is made just by noting the delta H and then noting the number in front of H2O2 and then assuming that's moles. So it's minus 196 kJs per 2 moles of hydrogen peroxide reacting. And so anytime I have a reaction, I'm just looking for the coefficient, assuming it's a mole for that particular reactant. And so that's what's telling me I need to go grams to moles for hydrogen peroxide. So hydrogen peroxide would be 2 times 1.008 plus 2 times 16.00. That's 34.02. And then I can use my conversion factor from my delta H that for every 2 moles of hydrogen peroxide that reacts, the heat that the reaction changes by is 196 kilojoules negative. We'll again think about the sign in a minute, but for now I'm just going to keep whatever the sign is for the delta H. So 5 divided by 34.02 times negative 196 is negative 28.8. So that's the Q reaction. So the reaction loses, because it's a negative sign, the reaction loses or releases 28.8 kilojoules of energy in the form of heat. Now, we tend to think of heat being released or gained in almost a way that it's usually a positive number. It's kind of like the analogy I like to use is money. Like, we tend to think of like how much money did you win or lose if you go to the casino. You don't usually say, what's your change of money? And your friend says, well, it's negative $200. You would probably say, well, I lost $200 or I won $200. So the word loss is implying the negative sign on that Q reaction being negative. So the reaction lost 28.8 kilojoules of heat. Heat's just something you tend to track in that fashion. Yeah. Oh, did I forget to divide by 2? Yeah. As soon as I saw a hand, I'm like, I did something wrong. I forgot to divide by 2 here. So I forgot the final step. So this should be 14.4. Thanks for catching that. It's always good to do the full calculation that you actually write out. So yeah, I forgot to divide by 2 here. So 5 divided by 34.2 times negative 196 divided by 2. So now we can have any quantity of reaction take place. If I have, however much mass of hydrogen peroxide is reacting, we just go to moles and then just use that ratio of minus 196 to 2 moles. So when you see a delta H of reaction, notice that there's no sign there's no per mole. It's like 196 kJs, and it's per 2 moles of H2O2, per 2 moles of water, per 1 mole of O2. So if you had said in this problem, what's the heat associated with forming 1 mole of O2 according to this reaction? Well, 1 mole of oxygen being formed from this reaction is 196. That would be the minus 196. So you can do this sort of problem with the perspective of forming so much massive product or reacting so much massive reactant in terms of just converting to moles and then using the proper coefficient of the delta H to that particular reactant or product. Okay, the next topic we're going to head into is like, how do we find these delta H's? We're going to find these delta H's primarily through experiments called calorimetry. So let's get into how we can think about calorimetry experiments. And what they're going to relate to is the study of heat changes, usually of solutions, usually of something like water or a reaction occurring in some kind of solvent. But we relate it to the Q by the MCS delta T. What this equation relates to is the mass of a substance times its specific heat times its temperature change is equal to the heat change. So heat is equal to mass, usually in unit grams, times the specific heat, which usually has units joules per gram degree C or joules per gram Kelvin. I'll talk about the difference in a minute and that they're actually the same unit. And then times our temperature change. Of course, that's T final minus T initial. The final temperature minus the initial temperature. So we'll do a numerical example on the next page, but this is the thought that if you have a certain mass of water, if you want to increase its temperature, you want to make TF higher, you want to make delta T positive, then heat has to be absorbed, obviously. So for temperature to go up for a substance, heat has to be absorbed. Specific heats are always greater than 0. They're positive values. They're not going to be negative. So every substance is going to have to absorb heat in order to increase its temperature or lose heat to reduce and lower its temperature. So if we want to lower the temperature of any substance, we're going to have heat being lost to have it go down in temperature. And so we see on the slide here for a couple of different substances, their specific heats. Now, they're listed joules per gram Kelvin, and I mentioned joules per gram degree C are actually the same unit because this is a delta T. A delta T in degree C, let's think of an example of 0 degrees to 100 degrees in Celsius. That delta T, so this is my T initial, this is my T final. So if we're going from 0 degrees to 100 degrees, my delta T would be equal to 100 degrees C. Well, what would that delta be in Kelvin? If you had said, Well, it's in Kelvin. Well, you might remember the Kelvin temperature is 273 plus a degree C temperature. So you might say, oh, the delta T would be 373 Kelvin. That would actually be incorrect. The delta T in Kelvin, we'd have to think, well, 0 in Kelvin would be 273.15 Kelvin. 100 degrees C in Kelvin would be 373.15 Kelvin. So the delta T in Kelvin would be 373.15 minus 273.15. That's 100 Kelvin. So your 0 to 100 degree difference in temperature, the delta in degree C, 100 degrees C, is the same delta in Kelvin. It's still 100 Kelvin difference in temperature. And so the incremental change to go up 1 degree is to go up by 1 Kelvin. So 0 to 100 is 273 to 373 Kelvin. The delta T's are the same. And for some reason, this is a big sticking point in this chapter. We see a lot of goofiness with converting and dealing with the fact some specific heats will be given joules per gram degree C or joules per gram Kelvin. Just know that they're equal to each other. So these specific heats are the exact same if they were given to you in joules per gram degree C. So the specific heats in those two units are synonymous with each other because the delta T's in degree C are equal to the delta T's in Kelvin. We'll try to point that out as much as it takes so you can see that worked out in a few examples so that we're not like double converting. So if you had said the delta T in Kelvin was 373.15 Kelvin, that would be a mistake. That wouldn't be correct for that 0 to 100 degree C difference. Now we see the specific heats for like nitrogen and aluminum as a gas, iron as a solid. Given here, you don't have to memorize any of these, but you're seeing generally that the metals have relatively low specific heats. A substance like liquid water has a relatively high specific heat. So this is why if you have, a pot of water on the stove, it's going to take it 10 to 15 minutes to heat up because it has to absorb a lot of heat in order for it to come up to 100 degrees C. If you took an equal mass but of a cast iron skillet, put it on the stove, it comes up to temperature much quicker because it has a lower specific heat. It doesn't have to absorb as much heat in order to increase its temperature. And so you also, one thing not on this slide is that the physical state will, the specific heat depends on the physical state. So if you look at water as a gas, water as a solid, water as a liquid, they each have separate and slightly different specific heat. So specific heat does depend on the phase of a given substance. So you have to kind of think if you need water specific heat, you need to think, what do I have? Liquid water, then I need liquid water specific heat. Okay, let's look at a couple problems here that relate to specific heat. So one of them is one like this here, where the specific heat of liquid water is 4.184 joules. Another way of writing joules per gram Kelvin is joules gram to the -1, Kelvin to the -1. So that's just another way of writing joules per gram Kelvin. And then another thing is that if you know the calorie conversion, like the joule to calorie, I don't know if you guys know it or not, but 1 calorie is equal to 4.184 joules. And it's specifically because the calorie is actually defined as a temperature it takes to raise 1 gram of water by 1 degree C. So a specific heat, if you look at the units, it's like if you had 1 gram to undergo a delta T of 1 Kelvin or 1 degree C, that's what the specific heat means. It's the amount of heat it takes 1 gram to raise its temperature by 1 degree C. So that is actually how the calorie scale was devised. We don't talk about calories too much in this class in terms of a unit, but you may notice that this happens to be, 1 calorie per gram Kelvin. And that's, you may say that seems odd, but that's actually how the calorie scale was, actually devised, was around the specific heat of water. Okay, so we're asked how much heat must be absorbed to increase a kilogram of water from 20 degrees to 95 degrees C. Okay, so this should just be an equation where we plug in Q is equal to MCS delta T. We just have to keep track of units here. So if I have a kilogram and my specific heat's in grams, I have to convert my kilograms to grams. Sometimes if I neglect writing units, I may miss this. So of course a kilogram is exactly 1,000 grams. Then I can use my specific heat. Let's make that 20 with like a decimal point so that the 20 has 2 sig figs so we don't get too caught up on sig figs on this problem. But I'm also taking the final minus the initial, so 95 minus the 20, because the water should have to absorb energy in order to increase, but this is 75 degrees C, and I can cancel. So that's one thing I like to do sometimes is just cancel the degree C in Kelvin and know that that's okay. They cancel each other because one of two things can happen. That I can either recognize that this is also 4.184 joules per gram degree C, that that's an equivalent unit, or I could have converted both of these to Kelvin, which why not? So let's take 95 plus 273. So if I want to convert that to Kelvin, that's 368 Kelvin. And then 20 to Kelvin would be 293 Kelvin. And then taking the difference in Kelvin would be 75 Kelvin, just like it was 75 degrees C. So again, if you're not sure, convert the two temperatures before the TF and the TI, both the Kelvin, take the difference and see that it's still 75 Kelvin. Okay, so we take, a kilogram times 1,000 times 4.184 and then times 75. So I get 313,800. So let's call this 310,000 to 2 sig figs. Joules, that's our unit here. Our grams have canceled. And then we can also write that as 310 kilojoules. Because, joule is 1,000 kilojoules. It actually didn't specify what unit to put this into in the problem, but kilojoule is probably the more, kilojoules might make more sense to write it in that unit. Okay, so now from just seeing that water can change its temperature from heat being absorbed, you may wonder, well, can we get the heat from something and relate that heat change to either an object changing its temperature or then later to like an actual reaction taking place in water? So one of the main ideas here will be that, well, if we have water, I can put something like calcium chloride or ammonium nitrate. Remember, those change the temperature of water. I could put a certain quantity into water where I carefully know how much, maybe do it within a cup that's maybe insulated from its outside so that we can try to keep all the heat changes to that particular open cup that we're going to track the temperature of. But our main calorimetry experiment will be where we have a thermometer probe to track water's temperature, where we can have a reaction take place in it, and we can try to figure out what actually happened in that cup and relate that to some chemical reaction or some sort of chemical change that was taking place. Okay, the first step will be, well, what if we just put a piece of hot metal? So what if I just start with, a piece of iron? I have 10 grams of it, so imagine just like a chunk of iron at 100 degrees C. So maybe I took a test tube. I had my iron in just an empty test tube and I put it in a boiling water bath. Boiling water is about 100 degrees C. So I just put my piece of iron in a water bath and I just leave it in there for, 10 minutes, long enough so that I know the iron certainly come to the same temperature as the water bath. And then I can take that piece of hot iron and just add it to a known amount of water just at room temperature, or say at 25 degrees C. So if we take that 10-gram piece of hot iron and add it to 100 grams of water at 25 degrees C, what do you think is going to happen to the 25 degrees C water? Is it going to stay the same? Is it going to drop? Or is it going to increase? It's going to increase in temperature because we just put something hot into it. And then how high is it going to go? How high of the temperature will the water go? Well, that's going to depend on the specific heat of iron, how much iron there is, how much of water there is, and its specific heat. So water's temperature is going to go up by however much heat it can absorb from the iron, but their temperatures will exchange until they're equal. So we're going to have the iron and the water exchange temperature until they thermally equilibrate, until they reach the same temperature. So thermal equilibration is nothing more than reaching the same final temperature. So what is the final temperature of the water and the iron once they have reached the same temperature as each other, using the specific heats that were that table before? I'll just write them here since I think remember irons was 0.45 joules per gram Kelvin, And then the water, the table listed as 4.18, but it's like, I usually like to include the 4 just because that's just rounded to 3 sig figs. So I usually like to go here since I know that the water is somewhat precisely known, because that's how like the calorie scale is defined and all that stuff. So I know water's pretty precisely is this, but we can check those in a table. You don't have to have those memorized. So you wouldn't have to recall that information. You'd have it given, or they're just asking us here to recall the table that we were already shown. And now this becomes kind of like a Q system, Q reaction, Q surroundings problem from before. Like we have here, not really a chemical reaction taking place, but we have maybe like a system that's changing, and the surroundings that are going to adjust accordingly. It doesn't really matter which one you treat as a system versus the surroundings. Like we can treat one of them as the heat, say, of iron, that it should be the opposite the heat change of water. You know, we're just thinking kind of one is the system, and then the other is the surroundings, where you just have that relationship of one of them is going to gain or lose heat while the other one does the opposite. And so what we know is that iron's going to lose heat because it's hot, so it's going to drop its heat because it's going to lower its temperature, and then water is going to increase its heat. It doesn't matter where I put the minus sign, because by putting the minus sign in front of water, I'm not saying it's negative, or that its Q is negative. I'm just saying that whatever the heat change of water is, it's the opposite of the sign of iron. So again, I can put this minus sign according to math on either side. Doesn't matter where I put it. So don't think that just because I write negative iron means I'm saying that, or excuse me, negative water, that water has to be negative. I'm just saying that if I write this expression here, if I write the MCS delta T, but for the iron, that's going to equal the negative MCS delta T for water. And we can move the minus sign over to here if we want. Doesn't matter where I put the minus sign, as long as it's on one of the sides and just one of the sides. Because the idea is whatever the heat being lost by the iron is being gained by the water. Okay, and so the only other thing I need to keep straight is using the mass and the CS of iron together with its delta T, and using the M and the CS and the delta T for the water on its side of the equation here. And so I had 10 grams of iron. The specific heat was 0.45 joules per gram Kelvin. And then I'm going to expand out my TF minus the TI, because I don't know what the TF is, but I know what the TI is. And I know my delta is just the final minus the initial. So that's just the initial temperature of the iron. I'm going to set that equal to, again, doesn't matter where I put the minus sign. Since I have it currently written on the left side of the equation, I'll keep that minus sign on the left side of the equation. I technically don't need these brackets because it's all multiplication, but I'll put the brackets there so you can just think it's the MCS delta T negative, and then have that equal the MCS delta T for water. So water, we have 100 grams. Specific heat, 4.184 joules per gram Kelvin. And then its delta T would be its TF minus 25.0 degrees C. Now, a few thoughts here. If this were a multiple choice test and I had some choices to choose from, do you think water is going to go up by a little bit or by a lot? Because iron is hot. Iron's a lot hotter than the water, so 100 degrees, 25. Do you think our final temperature is likely to be 60 degrees C, 50 degrees C? It's probably going to be just like water has to absorb a lot of heat in order to increase its temperature, and then iron didn't have to absorb that much heat to increase its temperature. So like iron doesn't really have that much heat to lose, and it takes water a lot of heat to increase its temperature. We're likely going to see a very small increase in temperature of water, maybe just a couple degrees. So we're not expecting a very big change in temperature. If I saw 4 choices and it was like 110 degrees, that's impossible. 50 degrees seems unlikely. 27 degrees, maybe. 21 degrees, it's not going to drop. So if we had 4 choices, we might be able to narrow down without even solving the math. But you can see the math is just a gory algebra problem. Like I just have to do some factoring and some solving here. So like I just need to take 10 times 0.45, so that's 4.5, and then times TF minus 100, and then have that equal 100. Let me keep the minus sign. I almost lost it. So the minus sign here, and then 100 times 4.184 would be 418.4 times TF minus 25.0. And so then let me just factor this in here. So that'll be negative 4.5 TF minus 450 degrees C. Probably not a problem to think about sig figs on. Let's maybe not worry about sig figs. That can be a topic for another day. But so, and again, I'm factoring in, but I'm not yet dealing with that minus sign. So maybe the brackets was helpful because I haven't yet put the minus sign in. I'll do that next. So then the 418.4 times TF, and then minus 418.4 times 25. So let me deal with the minus sign here. Let me just deal with this minus sign by getting rid of the brackets here and then changing that to a plus. Does that make sense? Because I just had, so I don't have to rewrite that whole step there. So I had the minus with the bracket, so it's minus 4.5, and then the minus times the minus 450, turn that to plus 450. And so now what I need to do is add 4.5 TF to both sides. So let's do that. So let's add 4.5 TF to both sides. And so that'll be 422.9. And then let me add 10,460 to both sides, which gets rid of that over here. So 450 plus 10,460 is 10,910. So I have 422.9 times TF should be equal to 10,910 degrees C. So my TF should be equal to 10,910 divided by 422.9, 25.8. I was just trying to think if I wanted to think about sig figs, and I don't think I do. So we'll leave the sig fig discussion out. That's a very good sig fig question, maybe the hardest one ever. But we end up with a final temperature 25.8, so just barely higher, because iron only has a specific heat of 0.45. It doesn't have that much heat to lose when it drops its temperature. It takes a lot of heat to increase water's temperature. So the final temperature here goes up by 0.8 degrees. So water increases by 0.8 degrees by adding this hot piece of iron into that water mixture. Now, a lot of algebra steps. Hopefully you just see that that's really just algebra of solving a complicated algebraic equation for TF so that we can identify that final temperature. Now the key here, if we saw that this temperature dropped, we know we made a mistake. If we saw that this final temperature was really high, we know that we made a mistake. So if we're being thoughtful, we can usually catch math mistakes on this type of problem. So see a few people writing. But our next question will be, or our next topic will be, well, what if we have a reaction take place inside of a container that's mostly, water? So like, let's say we take, a container such as this one here, which is just an insulated cup. I mentioned before that the isolated system was one that didn't seem to, if you recall, the closed isolated system can't exchange energy or matter with its surroundings. We've almost created that isolated system here, other than it's really not closed to the atmosphere. Like we have a piece of cork that's just meant to try to insulate the inside of the cup, but it doesn't really pressurize the inside, so it's still technically open to the atmosphere. So it's really not fully pressurized. But what we try to do is create an insulated cup so that when the, if we have a reaction take place that heat's being released and the temperature is going up, that the temperature stays in the cup. So we just don't want the cup losing too much temperature to the outside of the room before we have a chance to track the temperature. So we just create an insulated cup, a double cup, kind of like they give you 2 cups sometimes at Starbucks or whatever, is meant to just be extra insulating. So we use 2 styrofoam cups usually for this type of calorimeter. We often call this a coffee cup calorimeter. It's just meant to be like, imagine like a Stanley. That would be a perfect coffee cup. So it's not fully sealed because it's still open to the atmosphere. So we still have an open system, but it's also pretty well insulated. You have a thermometer probe so you can track the temperature of water so that you can see an exothermic reaction would make the water temperature go up. So the water is the surroundings of the reaction. So our exothermic reactions makes the surroundings go up in temperature, endothermic go down in temperature. So let's take a look at a common problem here, because what we can do is kind of like the iron example. You could add a piece of hot iron to this and try to see what the temperature change was. It is a way to find, you can find specific heats of metals that way. I think you guys will look at a lab where you try to treat the actual change of temperature of water as a measurable. Then from that you can solve for the CS, kind of the same problem we just did. But here let's take a look at a reaction taking place. Let's take ammonium nitrate, or excuse me, nitrite being added to 50 grams of water inside a coffee cup calorimeter. The temperature of the solid and water both we're assuming at the same temperature as each other of 25 degrees C before mixing. And then we mix the 2 grams of ammonium nitrite into that amount of water, and then the temperature of this cup lowers to 22.24 degrees C. So right off the bat, we see the temperature of the surroundings, the water, is dropping. So we know this is that endothermic type reaction. So we know right off the bat the delta H should be positive once that solid fully dissolves. So this reaction here should be one that we can see right off the bat is endothermic, and it's not exo. Exothermic should make the temperature of the water increase during that reaction. Remember, we're touching the surroundings with the thermometer. The thermometer is the surroundings of the reaction, not the reaction itself. And so what is the Q reaction? What's the heat of the reaction taking place inside of this calorimeter? Well, let's relate the heat of that reaction to its surroundings just by that equation that we've used a few times. The Q reaction is negative Q of the surroundings. That the heat change that the reaction underwent, that the reaction had to lose heat in order for the surroundings to gain the heat that it received to drop its temperature. That this being an endothermic reaction, that the reaction absorbed heat that it got from the solution, causing the solution to lose heat. So the reaction gains heat because the surroundings lost heat, therefore dropped its temperature. The surroundings is the solution. The solution is mostly water. And so we're told to assume that the specific heat of the solution is just that of water, because it's like 96% water. So we just assume usually in these problems that the specific heat of the solution is just that of pure water. And so my Q solution would be the MCS delta T, where all these are for the solution. So the mass of the solution, the CS of the solution, we're told to assume that's water, and then the delta T of the solution. And so my Q reaction is just then the negative, and the negative is just picking up that it's the opposite of the sign because the solution is the surroundings. So that's where I get this minus sign from. The mass of my solution would be 52.0 grams, and then times the specific heat of 4.184 joules per gram Kelvin, and then times my final temperature minus my initial temperature. I'll do the delta T. First 22.24 minus 25 should be negative 2.76 degrees C, and I'll cancel that again into the Kelvin because that's okay. So I do 52.0, or let me keep the minus sign, so negative 52.0 times 4.184, and then times negative 2.76. So of course that's where I get positive, that's where I get endothermic. So if I apply my negative sign correctly, that Q reaction is negative Q solution. And again, that's not saying the Q solution is negative necessarily, it's just saying it's the opposite of the sign of the reaction. Like every calorimeter problem, exothermic or endothermic, would start this way here. like regardless of exothermic or endothermic. Like that minus sign wasn't because this was endothermic. It's just because the reaction's always the opposite sign of its surroundings. The surroundings here is the solution. And so I work out here that my Q reaction is plus 600.5 joules. I think that should be good to 3 sig figs. Okay, now that's the heat of just the 2 grams of the compound reacting. So what is that the heat of the reaction of? It's the heat of that quantity of reaction. So you have to then think, if a reaction is taking place, and it's just a simple dissolution reaction, the reaction taking place is just the ammonium nitrite hitting water and forming ammonium cations and nitrite ions, because anything containing ammonium is water soluble. So the reaction taking place is just the simple dissolution reaction of that ionic compound into its constituent ions in water. So the reaction taking place is actually very, very simple. It's just the dissolution of an ionic compound. Now we're told here to calculate the delta H of solution of ammonium nitrite in kJs per mole. Okay, so how do we go from the 600.5, I just included an extra sig fig there, but how do I go from the 600.5 joules into the kJs per mole? So how do I get a number from joules into kJs per mole all of a sudden? Well, let me write my delta H would be equal to, and let's start with the 600.5 joules that we calculated with 3 sig figs, that's the joules per 2 grams of reaction taking place. Like what I divide by here is I have to identify whatever the limiting reactant was in the reaction. Now, we don't get too complicated. We could get complicated. There's a couple daily quiz questions that are probably harder than you'll ever see on the exams, because we can do chemical reactions inside of a coffee cup. I can take reactant A, reactant B, have some reaction take place just like this, pick up the heat change, and then relate it back to the delta H of the reaction. But I have to then think, well, which of the 2 reactants was the limiting reactant? And you can think, problems get really gory and can get really complicated when you have reactions of that variety taking place. Well, this solution here is really easy to identify the limiting reactant. So some problems could be complicated, could take some math, could be back to a chapter 3 or 4 problem to identify the limiting reactant. A few examples of those in the daily quizzes, but probably not that level of complexity. That would be like a 10-minute problem. So in order for you to solve a problem on a 50-minute test, usually we can't ask you that complicated questions on our exams. But all we need to do to go to kJs per mole is go from joules per gram to joules per mole to kJs per mole. So we just need to do the simple conversion. And we're given the molar mass here was 64.05 grams per mole. So that's how I get joules per mole, and then 1,000 joules per kJ. So if I just divide by 1,000, and then times 64.05, and then let's not forget the 2 here this time, divide by 2 grams. So I did the math really silly out loud, but 600.5 divide by 2 times 64.05, then divide by 1,000, and I get plus 19.2 kJs per mole. Now, the delta H of the solution, we're writing that as a property of the substance in kJ per mole. Now, what if I asked a slightly different question? Because it's really related. What if I said, well, what's the delta H of the balanced reaction of 1 ammonium nitrite going to ammonium plus a nitrite? What would the delta H of that reaction be? Well, there's just 1 mole of NH4NO2 in the equation, so that would just be plus 19.2 kJs without the per mole. So you just look how many moles are in the reaction, 1, so it's just 19.2. If we said, well, if you had 2 moles of ammonium nitrite to 2 moles of ammonium to 2 moles of nitrite, of course, then you would double times 2 moles to get to, that value times 2. So you can give a property of a substance, usually in units kJs per mole. So you're here defining the enthalpy of the solution process of the compound in units energy per mole. You can also relate it back to a balanced reaction, where you get rid of the per mole and just multiply it by however many moles there are of that reactant or substance in the reaction. Okay, so calorimetry problems, you just got to practice a few of them because there's not a lot of variability. Like the ways we can change these problems up are to, one, give you the exact same problem. So a lot of times you'll see problems are given in this exact same vein here, where we just tell you how much of a compound, what it is. Usually we give you its molar mass. We then give you the temperature change and ask you to solve for the delta H of the solution process, just like this here. We could also have given you the delta H solution, and then we could ask you to calculate the delta T. So if we give you the delta H of solution, the amount of solid, you can then use that to calculate what the delta T would be. Those are the two primary ways of asking this question. Either treating the delta H as the unknown and solving with the delta T for the delta H, or giving you the delta H and then having you solve for what the delta T or what the final temperature would be given an initial temperature. There's one other form of calorimetry that I'm going to kind of like quickly discuss because we rarely even test this, but I want to introduce it. It's on some daily quizzes, and you could ignore it on the daily quizzes, but we haven't asked a question on this topic in quite a while. But it's an interesting enough topic because it does involve a constant volume form of calorimetry instead of constant pressure. So in this form of calorimetry, you take a cell and you pressurize it with oxygen gas. So this container would be a fixed container that's completely sealed, has to be sealed, because we're going to have a sample with ignition wires that we ignite and kind of blow up or combust in real time, so that the sample burns, combusts, takes place. The inside of this container, of course, is going to get hot because you have a combustion reaction taking place inside of it. And then that hot container is going to make the water bath temperature increase. So this form of calorimetry almost always and exclusively studies exothermic reactions, because that's the whole idea, is you're detonating a sample of usually an organic compound or something that's going to react with oxygen and burn. So by nature, you're studying exothermic reactions, so the temperature of the water should increase because, again, the water is the surroundings of this reaction. And so the types of problems here usually give you a certain mass of compound that you put inside of this dish here that then was ignited by lead wires in the presence of excess oxygen, causing the calorimeter to change in temperature, usually going up, almost always going up. And so we know that this reaction here is exothermic, and that's the nature of reactions that tend to be studied by this technique. And then instead of giving you the heat capacity of the water or the specific heat of water, they give you like the heat capacity of this whole like calorimeter as a unit. So if you do this in the lab, I actually do this in my physical chemistry lab course, Chem 4410. If you're a chem major, which you probably aren't, but if you were, you'll actually do this experiment someday. It's a pretty fun experiment to do. But the way that the math works is actually pretty straightforward. Our Q reaction is still the negative Q of its surroundings. The surroundings is the calorimeter. And then the calorimeter is just the C-cal, the heat capacity of the calorimeter, times its temperature change delta T. So you would just be taking the heat capacity here times the temperature change. Notice that the heat capacity doesn't have a gram unit. So the 6 gram or the 1.50 gram sample does not come into play yet. Our Q reaction would just be equal to the negative 10.94 kJs per Kelvin, and then times the temperature change, which would be 6.589 is our delta, because it's 26.589 minus 20. So the temperature change is plus 6.589 degrees C. So our degree C Kelvin cancels, and then we get our Q reaction. So we get our 10.94 times 6.589. So I get negative 72.08. And then kJs, because it's already in kJs, and that's just the heat per gram. That's just the heat per 1.5 gram sample. And then you just use the molar mass to go to per mole. So to get the heat of combustion in kJs per mole, we're just going heat per amount of reactant that took place in the reaction and then converting to kJs per mole. I went really fast on this. You're never going to see this on a test. So don't worry too much about seeing this type of problem. Just understand that it's another form of calorimetry that has a sealed container, but then we solve it in a very similar fashion to the coffee cup problem. It's actually simpler in a way, but it's more complicated just because it's yet another example. So you'll see some of the daily quizzes. I wouldn't worry too much about the bomb calorimetry examples, but we'll pick up from here into the section on Hess's Law, the next section on Monday. All right, guys, have a great weekend.